These four head sections are for a Willys Super Hurricane flathead engine. The one on the left is a 6.86 to 1 compression ratio OEM cast iron head. It has a 90 cc combustion chamber. The next one is what I call a standard blower head. It has a 100 cc combustion chamber. Next is what I refer to as a fast burn head. It also has a 100 cc combustion chamber. Both of those two heads give a 7.5 to 1 compression ratio when used with a 31 thousandths inch thick head gasket. This last head section is what I call a tall chamber head. It is 743 cc's, and if installed on the engine, would give about 2 to 1 compression ratio. The purpose of this head is to eliminate the effects of valve shrouding and other combustion chamber design features such as roof height and transfer area. According to David Vizard, to completely unshroud a valve, the distance between the edge of the valve and the side of the combustion chamber should be equal to 0.2 times the valve diameter. In this case, using 1.65 inch diameter valves, the dimension should be 0.330 inches. On the standard blower head, that valve shrouding is about 30% of Vizard's dimension. On the fast burn head, that dimension is 50% of Vizard's dimension. And on the tall chamber, that dimension is up to 80% of Vizard's dimension. Going further would start to cut into the two stud holes. Those four heads will be flow tested to determine the difference in the flow characteristics. This shows the flow bench fixture used to test the four cylinder heads shown earlier. It's modeled from number 1 cylinder of the Super Hurricane engine. There's only the intake valve included because I didn't have any dimensional data for the exhaust valve. Not having it there may affect some flow, but the difference from head to head will not be affected. Everything except the fasteners is 3D printed. There are 10 3D printed parts in that assembly. The valve is lifted with the mechanism on the left. It uses a 1/2 inch 20 threaded rod. So the thread pitch is 50 thousandths of an inch, which means each revolution of the knurled knob raises the valve 50 thousandths of an inch. The valve and valve seat are also 3D printed. The valve guide is an OEM steel guide. The valve spring retainer and keepers are also the OEM parts. You can see how that's put together. The spring is a 13 pound per inch spring, which is much lighter weight than the OEM valve spring. I'll show how this works. The valve is fully closed. One rotation results in 50 thousandths of an inch. 2 rotations is 100 thousandths. 3 is 150. 4 is 200. 5. 6 is 300. 7. 8 is 400. And although the cam only lifts the valve for 20, we are going to test up to 500 thousandths, which would be right there. To bring it back down, to close it, just rotate it counterclockwise. You can see some of the, well, it is body filler on the 3D printed parts of the block. That is because parts that big, I have a hard time preventing a little bit of sag. So rather than sand all of that material off, I just filled it with body filler and sanded it smooth. The air horn is exactly the length of the intake runners, between the distance between the block and the log manifold that's currently on the engine. So the next step is to bolt this to a flow bench, install each of the heads, and determine the flow, and take a look at what we get from that.